So hello everyone, good day. So you're welcome back to our YouTube channel. So it is I once again, Sir Confidence from High Achievers Academy. So today we are going to be talking about digital logic design. So this is going to be an introductory video for you. So this course is relevant to those who are in the engineering field, those who are in the computing field, as well as mathematical field, those who are going to be building logical circuits. So this video is really meant for you. So if you haven't subscribed to the channel yet, please ensure to do so. So now let's look at what we have today. So today we are going to be discussing about the concept of logic design. We're going to understand logic gates and logic circuits, some special operations of logic gates, as well as their truth table. So now let's look, what are logic designs? So logic design is a system in electrical and computer engineering that uses simple number values to produce inputs and outputs operation. Now, all devices which you see, both your electrical devices in your home, they actually work based on input and output. For example, if you switch on a bulb, the the on switch button should lighten up the bulb. Then you press the switch again, the bulb goes off. So there is an input that we expect a certain output. We have input, or giving input to expect what output is. Like you going to the bank, the banking system, you press the button, the door opens for you, you enter into the bank. Or your home appliances, we use logic design for almost every aspect of electrical in electronic designs. Now let's dive more into logic design. So logic design is the foundation of how computers in digital circuits works. It involves designing circuits that process binary information, zeros and ones, using logic gates. Now the computer work with binaries, that's the digital form, zeros and one. So whatsoever input you are giving to the computer understands it in the binary form, that is the zeros and the ones. So with that that to say, we can actually look at the computer as a machine that processes digital processes our binary zeros and one. So in this course, we are going to be talking about zeros and one very, very well. So don't get confused when you start hearing zeros, you start hearing one. Why are we saying zeros? Why are we saying one? It's because the computer processes data in the digital form, the binary zeros and one, before processing and releasing an output which we users can actually understand. So every system needs input and output, like I said before. So in as much as the computers and our electrical components actually work with the binary information, so logic design is very, very, very important for you to understand as engineering and computing students. So let us dive down what we mean by zeros and one. So we have variable representation. In binary 1, it's for high, while binary 0, it's for low. So you have to keep this in mind. Whenever you hear binary 1, it's referring to high, we can call that a high voltage. Then binary 0 representing the low. So if you hear high, we can use 1 for high, or sometimes you can use 0 for low. So don't get yourself confused whenever you get the word 1 or high, or 0 for low. Now let's dive more deep into this. So let's talk about logic gates. That's the next category of where we are going to go in this video. So let's talk about logic gates. What are logic gates? So logic gates are building block of digital circuits. They perform logical operations on binary inputs 0 or 1 to produce a single binary output. So let's look at an analogy of logic gates to make you understand this better. So let's look. So you might think, what are logic gates? What are logic gates? So most, if you've not seen a logic gate before, you can go to the markets, ask for an IC. We always use IC numbers to represent logic gates. There is IC 7400, different gates. So what are logic gates? So for example, let's say we have a car, and that car won't start unless both key ignition is on. So let's say we have a car, the car won't start if both key ignition is on. So what am I trying to explain using a car as an example? Logic gates gives a connection for conditions in which electrical circuits operates. So for electrical circuit to operate, we have logic gates which comes in to determine how the input and output flow goes. So now we have different types of logic gates. We have different types of logic gates. We have the AND gates, we have the OR gates, NOT gates, the NAND, the NOR, XOR, and XNOR. XOR and XNOR. So we're going to be talking about each of these gates. We're also going to be talking about their truth table as well as a circuit diagram. We're going to be talking about a truth table as well as a circuit diagram. Now you could ask yourself, what is truth table? Before we proceed, you could ask yourself, what is truth table? So let us get a good definition for the truth table. So a truth table is a table used in logic and digital electronics to show all input combinations. A truth table is a table used in logic and digital electronics to show all possible input combinations to a logic circuit. So we're going to start with the AND gates. We're going to start with the AND gates. So the AND gates performs AND operation. Now there is a condition for the AND gates. So the output is high if all inputs are high. You can see we have 1 in the bracket here to so I can say output is 1 if all inputs are 1. So we can also say output is low if any one input is low. So let's look at it in the truth table here. This is a truth table. Truth table shows the outputs to all possible combination. So we say output is high if any inputs are high. So if I have input as high 1, A, which is an input, B is also an input, while Q shows the output. So here A is 1, B is also 1. So these two, both inputs are high. So we expect the output to be what? To be high. Then for the low, we say output is low if any one input is low. So I have here this input, A input is high, but B input is low. So I'm going to expect my output to be low. Here A input is low, but B input is high. I'm going to expect my output to be low. So here both inputs are low, my output is going to be low for this condition. So let's look at an analogy where I was talking about a car. So let's say a car won't start unless both the key is in the ignition and the brake pedal is pressed. So let's say a car won't start with 2 conditions. So those 2 conditions must be true before a car actually starts. So the way the AND gate work in such a way that 2 conditions is needed to be true before we can have a high output. So in real world relevance, we use the AND gate in decision making circuits where 2 or more conditions must be met. So it's commonly used in security systems, for example, where we can say when both key cards and password must be correct. So where we have conditions where 2 or more conditions must be correct before we can actually proceed. So also for some machines we use the AND gate for logical control. So imagine a machine would only start if all safety conditions are being met. So that is some relevance of the AND gates. So we've talked about the AND gate very well. Remember the truth table of the AND gate, and this is the circuit diagram of the AND gate. Keep this in mind because when we are building logical circuits, this is going to be very, very important. Keep this in mind. So let's look at the OR gates. Let's look at the OR gates. We've talked about the special use of the AND gates, allowing output when all conditions are true. It is used in control logic. We've talked about this. So let's dive down into the OR gate. So the OR gate performs OR operation, and the output is 1 if any of the input is 1, and the output is low if all input is low. So for example, I have here A is low, B is also low. My output Q is low. So A is low, B is high. My output is going to be high. So if any of the input is high, the output is going to be high for that row. So for this row, I have here A input is 0, B input is 1. Because from the condition, if any of the input is high, that is 1, the output Q is expected to be 1. So here I have here 1, A is 1, but B is 0. But we say that any of the input should be high for the output to be high. While for this last row, we have that both inputs are high, so the output should be what? Should be high. So this is the truth table operation of the OR gates, and this is the condition of the OR gates. So why this is the circuit diagram of the OR gates. So this is very, very important when we are dealing with building circuit diagrams. So let's look at the special case of the OR gate special use. So it is using enabling multiple paths for a signal or in an alarm system. So we can see if any sensor is triggered, the alarm goes off. So here we have different multiple paths for a signal, or you can say in a system whereby if any condition is said to be true, then we are going to execute a particular task. For systems like that, we use the OR gates. So remember the best example which we came out is an alarm system. That is, if any of the trigger goes on, the alarm system is going to go off. So that is one of the basic uses of the OR gates. That's one of the basic uses of the OR gates. So let's look at another gate. Let's look at the NOT gates. So the NOT gate performs NOT operation. Output is high if input is low, and output is low if input is high. So this is the circuit diagram of the NOT gate, and this is the truth table. So I have only just one input as well as one output. So looking at these two conditions, if A is 0, that is input A is low, we are going to expect that the output is going to be inverted. So A is 0, this is going to be inverted, the output is going to be 1. A is 1 is going to be inverted, the output will be 0. So you can see that the NOT gate is also known as an inverter. The NOT gate is also known as an inverter. So let's look at the special use of the NOT gate. It is used in creating signals, toggling states, and forming other gates. We are going to get across to forming other gates. But when we talk about toggling states, we want to change from one particular state to another state. That's what we mean by toggling states. I want to change from a state of 0 to a state of 1. So the NOT gate is relevant in this case. So we also use the NOT gate in a signal control system, especially a system where we need to stop or redirect a signal. The NOT gate is used in systems like this, systems where we need to stop or redirect a signal. Also in oscillators and signal generators, the NOT gate is being used in cases like this. And also the NOT gate it forms the foundation of complement circuits and toggle mechanisms. It forms the foundation of complement circuits and toggle mechanisms. So these are some relevance of the NOT gates, its real life application. We've talked about the real life application of the NOT gate. We've talked about the truth table of the NOT gate. This is the circuit diagram, and this is the condition of the NOT gate. Remember, if output is high if input is low, and output is low if input is high. So let's look at the next gates. So for the next gate, we are going to be talking about the NAND gates. We're going to be talking about the NAND gates. So the NAND gate performs NAND operation. Its output is high if input is high if any input is low. The output is high if any input is low, and the output is low if all input is high. So this is the truth table of the NAND gates. We have that from the condition here, we say that the output is high if any of the input is low. So I have one of the inputs here, A is low, B is also low. So both inputs are low. The condition says if any of the input is low. So but in this case both inputs are low, so we also expect the output to be what? To be high. Here A is low. The condition said if any of the input is low. So A is low, B is high. The output is going to be high because A is low. It meets one of the condition. And now we have here B is low, A is high, so therefore the output is going to be high. So for the last condition follows our last statement here, which says output is low if all inputs is high. So here all inputs are high, A is high, B is also high. So we have the output Q to be low, 0. And we see it is the inverse of the AND gate. It is the inverse of the AND gate. So for example, when we're dealing with AND gates, 0 and 0 should have given us 0. And the inverse of 0 is 1. 0 and 1 is going to give us 0. The inverse of 0 is 1. 1 and 0 should have given us, provided 0, but the inverse of 0 is 1. 1 and 1 should have given us 1, but the inverse of 1 is 0. So we can see that the NAND gate is an inverse of the AND gate. So it's more or less like we say not AND. So for more memory storage, you can actually say this should be not AND. So you can learn this using either these conditions, or you can understand it better using this analogy which I just gave. So the NAND gate is widely used in memory design. So example of memory, we have SRAM, we have DRAM. In the NAND gate is also found in processors and also used in control units. So one of the relevant use of the NAND gate, which is where we are going to go to soon, that is the sequential circuits. NAND gates are used in latch circuits. When we talk about sequential circuits, we are going to come to latches. So NAND gate is used in sequential circuits and is a basic building blocks for memory. It's a basic building blocks for memory. And more importantly, we have a special use of the NAND gate. The NAND gates are also called the universal gates. You don't need to forget this for exam purpose. This is very, very needed for exam purpose. The NAND gates are also called the universal gate, as they can be used to create other gates such as the OR gates, AND gates, and NOT gates. So we've talked about the truth table of the NAND gates. Remember that inputs, if output is high if any input is what? Is low. This is the circuit diagram of the NAND gates and the special use of the NAND gates. So let's dive deep down into another gate. Let's talk about the NOR gate. So the NOR gate performs NOR operation, and output is high if both input is low. Output is high if both inputs is low. So I have both inputs low here. We are seeing that the output is what? Is high. And we say output is low if any input is high. So this input is high, A is high. B is low, we expect the output to be low. A is low, A is high, B is high, yeah, we expect the output to be high. So this is the truth table of the NOR gates, and the truth table explains the condition very well. Remember that the output is going to be high when what? Both input is what? Is low. When both input is low. And if there's any input which is low, then we expect if the input which is low, the output is going to be high. That's the first condition. Then if any input is high, the output is going to be low. So let's keep that in mind. So the NOR gates are also called universal gates, as they can be used to create other gates such as OR gates, AND gates, and NOT gates. So we've talked about the NAND gate being a universal gate. We've also talked about the NOR gate being a universal gate. Very, very much important for exam purpose. Now, in the real world relevance, NOR gates are a very key factor, a very key structure for microcontroller architecture, MCA. They're used for microcontroller architecture. They're also used in reset logic. So that's why they are used in the RS flip-flop. You can see the SR flip-flop. We've not gotten to that yet, which we're going to get down to sequential circuits. So we have the SR flip-flops. The NOR gates are used in the building of the SR flip-flops. So they're also used in light controls and toggle switch. So they're also used in light control and toggle switch systems. So we've talked about the NOR gate truth table. This is the circuit diagram of the NOR gate. Talk about the conditions and the special use of the NOR gate. So let's check out the next gate. Next gate is the XOR gate. So the XOR gate, for the XOR gate, we have that output is high if odd number of inputs is high, and output is low if odd number of inputs is low. Output is low if odd number of inputs is what? Is low. So this is the condition. This is the condition of the XOR gate. So there is a trick to the XOR gate in case this is difficult for you to actually memorize. So you can actually take an addition, a binary addition for the XOR gate. Is a trick which you can use to learn the XOR gate. So for example, we can say 0 plus 0 will give us 0. The binary case. We can say 0 plus 1 will give us 1. We can say 1 plus 0 will give us 1. And we can say 1 plus 1. Remember the binary, we do say 1 plus 1 will give us 0, remainder what? Remainder 1. So it's like we use such very simple case to actually paint the XOR gate so it doesn't look confusing for students. So you can either learn from the condition or you can follow the trick which I just pulled out here. So we've talked about logic design. We've talked about logic designs. We've understood logic gates and logic circuits. So in this video, we've also talked about some special operations of logic gates as well as the truth table. So I believe that at the end of this video, you should have learned all of these. So coming back to our learning objectives, at the end of this video, you should have understand the concept of logic designs. You should have understand logic gates, the AND gates, the NOT, the XOR, the NAND gates, NOR gates, the logic circuit diagrams which I showed you, which you have to know that because it's very, very important in building logical circuits, and also special operations of logic gates, which you have to understand in building complex designs, as well as truth table which shows the output of all possible combinations. So we've talked about all of this, and I believe that this video was helpful to you in your journey in logic design. So if you've not subscribed to the channel yet, please ensure to click on the subscribe button and hit the like button. So in the next video, we are going to be looking deep into Boolean algebra. We're going to talk about K-maps. We're going to talk about canonical form of Boolean. We're also going to talk about, then I'm going to dive deep down into sequential and combinational circuits. So see you in the next video. Thank you.